Good morning, everyone. Firstly, I'd like to thank all of you for choosing this lecture and for inviting me to come and present today. As was explained to you, I want to focus on human spaceflight. In the 57 years since humanity has actually ventured into the cosmos, what have we achieved? What are the challenges? Where are we going in the future, and what lessons have we learned? Now, one thing I want to point out at the beginning is that I've got a number of different hats on, as you can see, but all of the opinions that I'm going to be expressing are purely my own. They are personal. Now, when we think of space, we need to remember that the internationally accepted boundary of space is much closer than we realize. Space is only 100 kilometers from where we are now, 62 miles. It's closer to where we are now than the distance I've come down this morning from Leicester. But that 100 kilometers, of course, is straight up. And if we want to get up there, we've got to battle, in terms of gravity, against a force that's dominated the way that life's evolved on this planet for billions of years. If we want to stay in the space environment, we are dealing with an environment from a radiation, from a thermal, from a pressure point of view that's far more challenging than anything we experience here on the surface of the Earth. Even though we've been doing it for more than 60 years, it's still pushing our technology to the limit, but when we get there, the view is literally breathtaking. Here we've got accelerated footage taken from the International Space Station. And what I love about this is not only do we get a new picture of the cosmos, we get a new picture of planet Earth itself. We can see the development of societies and civilization. We have a living physics lesson when we look at how the solar wind interacts with Earth's magnetic field and then rains into the upper atmosphere, producing the aurora borealis and australis, the northern and southern lights. Little wonder then that when you see imagery like this, we are all captivated. We all want to go into space. But don't believe the media hype. The number of people who've ever had this view would comfortably fit into one Airbus A380 Super Jumbo, and 19 of them have died in the process. We've got some amazing technological and engineering challenges, and one of the biggest ones is how we get to these mind-boggling velocities to stay in Earth orbit. No matter which rocket system we look at, here we've got an Ariane, we've got Long March, and we've got a Soyuz rocket launcher, we are relying on enormously high-yield exothermic chemical reactions, using a fuel and an oxidizer and trying to control the energetic equivalent, in some cases, of a small atomic bomb, and to ride that on our journey into orbit or further out than that. That's just one of the challenges, but the problem with this image is you don't get an idea of scale. So on this next one, taken a few years ago, you could see me, when I was less follically challenged than I am now, against the granddaddy of all rockets, the American Saturn V. This particular one that was never used is on display at Johnson Space Center in Texas. So what was the driver for human space exploration? It was good old Cold War politics. When we think, after the carnage of World War II, with global destruction, what emerged from the ashes was this geopolitical battle between two competing ideologies, communism, capitalism. And what better stage to show your superiority than the ultimate high frontier? This was the origin of the space race. And it's fair to say that on October the 4th, 1957, the United States took a massive body blow to its pride when we had the launch of the world's first satellite, Sputnik 1. Seemingly primitive, and yet every day it was passing over US territory with triumphal impunity. Wind forward 3.5 years, April the 12th, 1961, and the Soviet Union launched Yuri Gagarin to just about complete one orbit of the planet and land a worldwide superhero. And this, arguably, was the incentive for US President John F. Kennedy to set one of the most audacious national goals that has ever been set in any country, the challenge of sending a human being and return to the moon and returning to Earth safely within a timescale of 9 years. Now, you might read that this was regarded as impossible. That's not the case. It was engineeringly and scientifically possible, but right at the limit of what we could achieve. And most importantly, it was going to need a concerted effort of nearly 500,000 scientists and engineers and a massive infusion of finance. Now, finance doesn't solve all scientific challenges, But it's quite interesting that in the 1960s, at the height of its budget, NASA was getting 5% of the US federal budget, more than 10 times what it gets now. And of course, we all know what happened. In the 1960s, the US accelerated ahead in its destination of getting humans to the moon. Now, one of the things we need to remember when we see wonderful imagery like this from NASA's Deep Space Climate Observatory of the far side of the moon transiting in front of the Earth, and when we see diagrams like this of the Earth-Moon system, you know, the language of mathematics about the distance between the Earth and the Moon and the size of the Earth and the Moon tells a very different story to this sort of image. This is not to scale. And we always need to remember that if the Earth is this big, the Moon isn't here, it's not over here, it's way out over there. When we look at the Earth-Moon system to scale, the Moon is 1,000 times further away than the orbit of the International Space Station. That's just one of the challenges that we must remember. And of course, the previous speaker talked about 50 years since the Apollo 8 mission to the moon. You know, I always think of these Apollo voyages between 1968 and 1972 as being the most audacious voyages of exploration that the human race has ever embarked upon. Those 24 human beings who went to the moon and the 12 who landed are still the only members of the human race to have explored directly, rather than vicariously, an alien world. And when we look using lunar reconnaissance orbiting imagery, we can see the footprints, we can see the vehicle tracks as if they were made yesterday. With no atmosphere on the moon, those footprints are going to stay for millions of years. We have truly left our mark as a species on the cosmos. And in December 1972, we stopped exploring. And we may ask, why? Well, from the US perspective, the Vietnam War was going on. The goal had been achieved with beating the Soviet Union to the moon, but the race was on to try to make space more accessible, because the trouble with normal rockets is they're single use. The booster stages rain down into the Atlantic Ocean or onto the deserts of Kazakhstan, so the US were trying to build a partially reusable space shuttle system. From the Soviet Union's point of view, it was no longer about racing to the moon, which they lost, but it was about living in space. Can we spend a month in space, 3 months in space, 6 months in space, a year in space? And this, of course, culminated in the crown jewel of the Soviet program, the MIR Space Station. And I love showing this image because it is a salutary lesson in how quickly things can change. When I went to university in 1987, if you would have said to me at the height of the Cold War that I would see the MIR Space Station docking with the US space shuttle Atlantis, I would have gone, no way, this would be impossible. But 3 years after I had those thoughts, when I started university, the Soviet Union collapsed, and we began to get the opportunity for collaboration. That's what led to the US-Russian collaboration with the MIR program, and of course, this was the forerunner of the International Space Station program. This is one of my favorite views of the ISS here. You can see the photovoltaic arrays that generate electrical power from sunlight. Could you put your hands up, please, if any of you have seen an ISS pass when it passes over the sky? Okay, we're getting quite a lot of people. The very best ISS pass happens when it's dark on the Earth, and so it's at dawn or dusk, just before sunrise, just after sunset, and the ISS itself is still in sunlight, just in this image. And when you see it, what you'll see is it's an incredibly bright object, almost as bright as Venus. It'll get up for the astronomers to magnitude -3.5 sometimes, and then suddenly it goes into shadow, it goes into eclipse, and it disappears. This picture shows it incredibly well. And in terms of the scale of the space station, I just want to show you this animation that was made by some of my colleagues. This is an enormous structure. It's got a mass of nearly 500 tons. It was assembled on over 30 different missions, and the first components were sent into orbit in November 1998. Parts of the space station are nearly 20 years old. Many of those components never met on the Earth. The first time they ever made physical contact was when they were in orbit. They docked together while traveling at a speed of nearly 5 miles every second. Now, this gives you one perspective of some of the challenges, and you'll often read that the ISS is a wonder of international collaboration. The pragmatic truth is a little bit different. It was driven by political necessity, because after the collapse of the Soviet Union, the United States were incredibly worried about control of all of the expertise in the Russian program. Was there a way of able to have some funding that would enable some semblance of control, but also to make use of the Russian expertise? Because the Soviets/Russians were masters of long-duration spaceflight. Many of you will remember Mikhail Kornienko and Scott Kelly's year-long mission in space from a couple of years ago, 342 days. On the Mir Space Station, a year in space was done nearly 30 years ago. In fact, it's the longest ever spaceflight, 438 days, wasn't done on ISS. It was done a quarter of a century ago on the Mir Space Station. And what I love about this particular view, we will never get something like this again, because this is the US Space Shuttle docked onto the ISS structure. This is pretty much what it looks like now. And of course, the Space Shuttle is no longer flying. And my favorite image of all from the Space Shuttle program is this one. And one of the reasons I love this is it shows just how much the human spaceflight experience has changed since the 1960s. If we took an image like this in the 1960s on the Earth, with one exception, Valentina Tereshkova, it would have been all male, it would have been military test pilots or scientists, engineers working with the military, and virtually all of them would have been originally from a European background. We now see global agencies involved. We see people from all sorts of different professional backgrounds. In this image, we've got former scientists, former engineers, former doctors, a former school teacher with Dottie Metcalf-Lindenberger. It's true to say now the human space experience is so much more inclusive than it was when I was born in 1968. And of course, the entire country was captivated when Tim Peake became the first British astronaut flying for the European Space Agency. We must never forget, though, that 25 years before, Helen Sharman became the first British astronaut in space when she visited the Mir Space Station. And what a lot of people don't realize is that if it wasn't for the British government's former position that's now changed on human spaceflight, it is likely that Helen would have had multiple missions flying for the European Space Agency, because she was put through to the final stages of a number of European Space Agency astronaut selection processes after her flight, and the only reason she didn't get selected was Britain didn't participate. So what do astronauts actually do in space? Well, they've got three priorities in this order: keeping themselves healthy, keeping the space station healthy, and only after that do they do their primary job of conducting research on behalf of scientists from around the world. On the left-hand side, you can see Italian F-16 pilot Samantha Cristoforetti, a current ESA astronaut, exercising on a treadmill. The human body is lazy. Put it in a microgravity environment, bones start weakening, muscles start atrophying. 2 hours exercise a day at a minimum. If anything goes wrong on the space station, you've got to fix it yourself. And what you're going to see now, accelerated, is the least glamorous side of being an astronaut. This is a 2-hour repair job on the space toilet. The ISS actually has two, which breaks down with alarming regularity. So once you've kept yourself healthy, you've kept the space station healthy, then you do your primary role of research. So how do you get an experiment onto the ISS? Well, my team were fortunate enough during Tim's mission to be tasked by the European Space Agency with developing a new physics education set of experiments to be conducted on the ISS. It's not just the case that you build your stuff, put it on a rocket and blast it into space. You've got to subject your payload to a battery of tests to show it's not going to shake itself to pieces during launch, to show it's not going to outgas for 6 months that it's on board this sealed environment of the ISS. You've got to write the procedures for it. Even something as simple as the equipment that we sent, we had to do 6 months of testing. And just before Tim launched, you could see myself and my colleague Andy McMurray spent 2 days in Germany at the European Astronaut Center training him up on the procedures for our experiment. Tim had to do this for 140 experiments that he did during his increment on the space station. You can see some scenes of the vibration testing that we did for our payload when we had to duplicate the vibration environment as much as possible of the rocket that we were launching on, which was a SpaceX 7, a Falcon rocket. Once we had completed that, we got our boarding pass. This was our flight safety certificate. And 6 months before Tim was launching, on the 28th of June 2015, our cargo, along with 4 tons of other cargo, was sitting in that Dragon capsule on the top of that rocket. I've never launched a payload into space before, so myself and my colleagues were watching, and everything seems to be going fine until 2 minutes after launch. We get a catastrophic failure of the second stage, and instead of going up to the ISS, our payload rains down into the Atlantic Ocean. Now, to say my heart hit the floor is an understatement. But of course, in space, we've always got a plan B. We had a backup payload that had been tested to exactly the same standards. We managed to hitch a ride on a Russian Soyuz launch 3 months later in September. Tim was launched in December, and then we awaited for our slot, our opportunity to conduct our experiment. And it came at very short notice. I got a phone call in January on a Monday at the beginning of the week saying, can I get out here to the European Columbus Control Center in Germany? Can I get out there on a Friday? You've got your 4-hour slot for doing your experiments. And I said, look, I can't do this at short notice. And thus began probably the most surreal experience of my career, because what they actually did is linked me up through the Eurocom Center to the ISS from home. And so I was Friday working at the Space Center. I went home. I linked up. We had the external monitors there. We had Tim coordinating his stuff. I was coordinating my stuff just before we started. And here we are ready to go. Couldn't believe it. And all of a sudden, my little lad appeared on the scene. Starts wondering, what's going on downstairs? I'm thinking I'm about to start the experiment run. We've only got 4 hours. You know, go away. But he wasn't having anything of it. And in the end, I just had to sit him down. And I think he's still got a record for being the youngest person to link up live with the ISS. He just kept in the background. And my wife was taking the picture. Everyone in mission control was laughing. I was the only one who was getting a little bit stressed out, thinking things are going wrong. Sahil, just move away. Eventually, he did. And what I want to show you is just a musical pastiche of some of the experiments that we did. We wanted to do physics demonstrations for teaching on orbit in a way that hadn't been done before. Now, we did a total of 65 experiments. I'll show you a few snaps, and I'll show you where you can find them as well. So, classical demonstrations of phenomena straight out of the A-level and first-year university teaching syllabus: kinetic theory of gases, Newtonian mechanics, momentum and collisions. You'll see that we've got a grid behind us that was actually blocking the airflow in the Columbus module, the behavior of diatomic oscillators, and we were filming in X, Y, and Z directions with HD cameras. Now, so far, you may have seen stuff like this before, but what we then did was every data set that we had, we dynamically analyzed. Not only video capturing it, but putting it into a format that students at school and university level can select the parameters that they want to measure and that they want to start understanding. So instead of being served on a plate, students can get interactive and do their own analyses. Now, for this project, Tim and my colleagues also narrated a number of films while Tim was on orbit. We wrote a number of teacher guides, and all of it is available there online. So the ISS has been a wonderful platform for education, for inspiration, but most of all, for engineering and science research. But what about the challenges of getting into space? And I want to go back now, nearly 30 years, in fact 32 years, to the 28th of January, 1986. This was the 25th launch of the United States Shuttle program, and this is the Space Shuttle Challenger. Now, as I talk through the launch, what you'll see here is you've got an orange fuel tank with 600 tons of liquid hydrogen and oxygen, and strapped to the side, you've got the world's largest fireworks. Solid rocket boosters with aluminium as a fuel and with ammonium perchlorate as the oxidizer. And on this mission, there were 7 astronauts, including the first teacher in space candidate, Krista McAuliffe. Now, by this time, the shuttle mission program was in full drive. There had been 10 launches the previous year. NASA was under tremendous pressure to meet its schedules, and everything seemed to be going fine. The whole of the United States was watching this because of Krista McAuliffe's involvement.
3 engines running normally, 3 good fuel cells.
The engines have throttled back as we go through the period of maximum aerodynamic stress on the vehicle going near the speed of sound.
Per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
The engines throttle back up to 100% of full power. There's a wind shear encountered at 48,000 feet.
Up, 3 engines now at 104%.
Challenger, go with throttle up.
Challenger, go with throttle up. 1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles.
We had a catastrophic failure of the entire system and the death of 7 astronauts. Now, it turned out that the fate of Challenger was sealed with the launch decision, which many engineers had been arguing about. They had worried about the viability of launching at an incredibly low temperature. I won't go into the engineering schematics, but it was an issue with the solid rocket boosters and the O-rings that sealed them together. One of the O-rings had failed. We can see it there. There was flame leaking out. You'll often hear that Challenger is described as an explosion. It was not a thermodynamic explosion. What happened when that solid rocket booster, you had the leak from there, it swung around, ruptured the fuel tank, and what you can see is the force of 600 tons of liquid hydrogen and oxygen vaporizing. Now, as far as the shuttle vehicle was concerned, it didn't care whether it was an aerodynamic explosion or whether it was a phase change overpressure. Catastrophic breakup of the vehicle and death for the 7 astronauts. And here you can see the scale of that plume taken by one of the Earth observation satellites in equatorial orbit. This was a mistake, a disaster that was completely avoidable because engineers had warned about it. And 17 years later, at the different part of a flight cycle, we had a similar calamity. This was the flight of STS-107, the 113th mission of the shuttle program and the first with an Israeli astronaut. It conducted a 16-day science mission. The science return was incredible, but its fate, once again, had been sealed during launch. Because during launch, it was noticed that a load of very low-density insulation was coming off the orange tank and impacting on the underside. You can see some flecks of it coming off there. Now, some engineers were worried about this, but other engineers were saying, no big deal. This sort of thing has happened before. This is low density, foam packaging. What damage can it do? As we found out after the disaster, even that low density material hitting the shuttle's thermal protection system was enough to create a catastrophic breach. Now, you won't notice this during launch, but you need to remember when you're coming back to the Earth, traveling at a speed of 5 miles a second, what's often called friction, but is actually ram air compression, will cause your outside temperatures on your vehicle to reach thousands of degrees centigrade. You need thermal protection. And just after launch, when this hole was made in Columbia's thermal protection system, the vehicle was doomed. The crew knew nothing about it for 17 days, and on the 1st of February 2003, during re-entry, high-temperature plasma gets in, weakens the structure, the vehicle topples out of control and broke up over Oklahoma, Texas, with debris raining down over thousands of square miles. Again, totally avoidable. But there is another issue that we need to think about, and it's the challenge of staying alive. Down here on the surface of the Earth, we take the atmosphere for granted. But we need to remember that when we look at the figures that we use for atmospheric pressure, what they are telling us is that we are living at the bottom of an ocean of atmosphere that's extending for hundreds of kilometers above our heads. The ISS is still in Earth's atmosphere. Now, when you look at the numbers, as a physicist, what that tells me is that on every square meter of ground, there is the weight of 10 tons of atmosphere on me. And the only reason I'm not completely squashed by this is that I'm internally pressurized with gases pushing outwards. As humans, we don't notice absolute pressure, we notice pressure differences. And as you go higher in the atmosphere, the air pressure gets less and less because there's less weight above you. So what would the effects be on a human? Well, there's 2 ways that we can show that. And this is a demonstration that you can do with syringes that you have at home, but I've got a big glass demo syringe. And I'm going to use these marshmallows as my simulated astronauts. Like us, they're full of gases that are exerting outward pressure. And the thing about a syringe is, this is a Sunday, I don't want this to degenerate into a physics or chemistry lesson. But all you need to remember is if I've got a fixed mass of gas like this, And if I increase the volume, the air pressure gets less. So when I do this, it's as if I'm going to a higher altitude, higher and higher above the Earth's surface. And when I put my marshmallows in, as I say, for this particular one, it's much better if you try it at home with a syringe. When I seal it, what you can see as I pull down is these marshmallows are starting to swell up. Can you all see that down at the front there? Try it at home yourselves. So you do this, seal it, the marshmallows start swelling up. If I equalize the pressure, they shrink back down to their size. So the first thing, expose yourself to low pressures, you're going to start getting swelling of your tissues, massive swelling of your tissues. That's a problem. But there's an even more insidious effect. What I've got in this flask is I've got water that's hot, but it's not boiling. It's probably at about 70, 75 degrees centigrade. And when I take my glass syringe, I'm going to extract some water, I'm going to keep a tiny amount of air at the top, and I'm going to seal it up. That water is definitely not boiling. Now, there is no way that I can supply heat energy to this system, but as soon as I reduce the pressure, can you see it's starting to boil away furiously? Okay, as soon as I equalize here, that stops. Now, that's just a dramatic demonstration of how the boiling point of water depends upon the atmospheric pressure. Why is this so important for human survival in space? This is a simplified explanation here, but when you've got water in the liquid phase, if you've got lots and lots of atmospheric pressure, it's very hard for water molecules to escape from the bulk of the water and evaporate away. Of course, water will evaporate at all temperatures in the liquid phase, but it's at 100 degrees centigrade where you get this mass escaping. And I know I'm missing out the issue of gases coming out of solution and so on. I'm keeping this simple this morning. If I reduce the air pressure, though, with less gas molecules above, it's easier for the water molecules to escape. And at one level, that is why the boiling point of water reduces when the atmospheric pressure reduces. Now, I must apologize because I've kept graph-free until now. This is the only slide where I've got graphs. And what I'm showing on the left is that as air pressure reduces, the boiling point of water reduces. On the Earth, air pressure is 100 kilopascals. Water boils at 100 degrees centigrade. On the summit of Mount Everest, the air pressure is about 30 kilopascals. Water boils at maybe 65, 70 degrees centigrade. Now, when we look at what happens in Earth's atmosphere, the higher you go, the less the air pressure. And when you get to an altitude of 20 kilometers, the boiling point of water is 37 degrees centigrade. And I think you can see the significance of that figure. That is the aeromedical boundary of space. You go to that altitude, you need a pressure suit to keep you alive. Now, there are lots of myths about your blood boiling away in your veins and so on, and your body exploding if it's exposed to low pressure. That's not the case. But what will happen is any liquid that's exposed to that pressure in your lungs will expand 700 times and shred your alveoli. You'll get catastrophic outgassing of the gases dissolved in your blood, and you're going to have a pretty nasty death. And that's why when we look, for example, at Joe Kittinger and his stratospheric balloon jump in 1960 from 100,000 feet, he was the first person to ever directly experience the space environment. And when we look at Felix Baumgartner's similar jump 52 years later, you can see they are wearing full pressure suits. And if anybody wants to see the sort of helmet that Kittinger used and try it on, my colleagues at the University of Leicester will have it after this lecture. So that's the challenge that we have for pressure suits. And this is what happens if you lose pressure. This is Jim LeBlanc, a spacesuit engineer, testing in a vacuum chamber. His suit failed. I'll just show it again. They flooded the chamber with oxygen when he passed out, and he says that the last thing he remembers was the saliva boiling off his tongue. Now, he was lucky. These guys were not so lucky. This is the crew of Soyuz 11 in 1971. They did a 22-day mission to the world's first space station. Their capsule returned safely to Earth. The Soviet recovery crews came, and they were dead. And the reason they died is their spacecraft depressurized during re-entry, and they didn't have spacesuits. That's the reason why Tim, during launch and landing, was wearing one of the so-called suits that you can see here. And I'm delighted that my colleagues at the British Interplanetary Society have also got a so-called suit that you can have a look at there. Now, I couldn't bring our so-called suit, but what I've brought is even better. This is one of a kind, certainly in the UK. It was a suit that was designed for the Russian space shuttle program, Buran, and it's what I call the so-called spacesuit on steroids. Now, when I first got this suit, I was showing it to everyone who came by my office, and that's Paolo Nespoli, an Italian astronaut flying for the European Space Agency. He was absolutely amazed. He said that this suit is even better than the one that I've been issued to fly with. But what I didn't bother to do was a pressurization test. So after I had it for a year, I decided, let's see if this holds pressure. And what I'm now going to do is pressurize this suit, and you will see over the next minute or two just how dramatically it changes in appearance. This particular suit, the reason why it's covered in this material here is it's not just designed to keep you alive if your spacecraft loses atmospheric pressure, it's also designed to keep you alive if you were in the Russian space shuttle and you had to do a stratospheric ejection during launch or re-entry. And already, as we start inflating it, it's coming alive almost. And when I stand it up like this, you can see it's completely changed in profile. Now, this sort of suit is not designed for a spacewalk. This is designed purely to keep you alive if your spacecraft loses pressure. And once again, if anybody wants a closer look at this particular suit, okay, I will have it on the University of Leicester stand a little bit later. Now, I'm watching the clock, and I'm determined not to break my time limit, so I'm just going to accelerate onwards and put Igor here onto the seat so that he can have pride in place. And hopefully he won't just slump down and lose pressure. One last thing involving spacewalks. If you go on a spacewalk, expect the unexpected. This is Luca Parmitano, one of Tim Peake's colleagues, taking, a selfie, a wonderful image here. 20 minutes after he took this, he was fighting for his life. His spacesuit internally had started to flood because of an issue with the coolant loop, and he started to get water building up in the helmet. He managed to get back into his airlock in time to prevent a drowning incident, but this is the closest we have come to death on a spacewalk. In space, we've always got to expect the unexpected. And when we look at human spaceflight and all the incidents that have happened, it's clear that no matter how good we get at it, we are always pushing the realms of what we can achieve. There will be future deaths in spaceflight. It's something we've got to live with. All we can do is try to reduce the risk. We will never bring them down to zero. And I just want to share with you an image that NASA certainly don't like me sharing. Well, it's out there, so you can share it. This was an image that was taken after a collision with the cargo vehicle with the Mir Space Station. The crew survived. They were very, very relieved. And of course, the Russian psychological cure for when you're relieved is you need to have something that's going to ameliorate the mood. This is booze and cigarettes being smoked on the Mir Space Station. This doesn't go on the ISS, but if anybody says, has anybody had a cigarette or a drink in space, the answer is yes, we've got the photographic evidence. And in my last 7 minutes, what about the future? Emerging space powers, China. I'm fortunate enough to be heavily involved in the UK-China strategic program of collaboration in space science, and I've been honored to be working behind the scenes on a lot of their facilities. China has really accelerated away. The first human spaceflight from China's program, Yangliwei, 2003. The first space station was built, Tiangong-1. The first Chinese spacewalk. A lesson from space was broadcast to 60 million students. And having seen the Chinese facilities, their Hydrolab for spacewalk training, their new launch site on Hainan Island, it is as good as anything we have here in the West. The components of China's next space station have already been built. They have shown successfully the techniques for rendezvous and docking. And within 3 years, this will no longer be a model in the Astronaut Center of China. This will be China's multi-modular space station, operational from 2021. And our goal at ESA is to get European astronauts flying on that station in addition to flying on the International Space Station. We've had the first training exercises last year in participation with China. What about going up to the ISS? We're about to see the taxi services from Boeing CST-100 spacecraft, from Elon Musk's crewed version of the Dragon spacecraft. And for ISS itself, it's getting old. Some components have been up there since 1998. All bets are off after 2024. We still do not have agreement on what will happen funding-wise. Now, we are planning for operations up to 2030, but it may be that the Russian segment is taken off and becomes a free-floating space station. In terms of where humans are going to go, this is the next generation. This is a plan that has changed name many times and is now being called the Lunar Orbital Platform Gateway. It's not a big station. It's a small, remote facility that's going to be in deep space, in an orbit in the lunar region, in cislunar space. And we are going to see the components for this small station, you can see the size of it here, being launched over the next 10 years. It won't be permanently occupied, but for the first time, we will have crews of astronauts, including Europeans, for up to 30 days in deep space. And this is essential if we're to go elsewhere in the solar system. Everyone has looked at Elon Musk's plans. What are his vision that he has here? Here you've got a representation of the American Saturn V rocket, the Falcon Heavy rocket, and Elon Musk's new big Falcon rocket that he's talking about. I think many of us were watching when the Falcon Heavy flew, and it was incredible because you had a single booster stage that blasted a payload into an orbit going around the sun, and you had flyback of the other two boosters. And even someone like myself, who's a little bit of an Elon Musk cynic, was absolutely blown away by the sort of balletic, poetic dance of these two boosters coming back and landing on the launch pad for reuse. This was incredible in terms of spectacle. It was also incredible in terms of engineering. What you think of the idea of what this rocket did, which is blasting that Tesla Roadster on a heliocentric orbit, going out to sort of Mars's distance from the sun. Was it folly? Was it an amazing piece of artwork? Who knows? But you'll also have seen, probably last week, that Elon Musk has announced that his new vehicle, the big Falcon rocket, will take a group of artists led by a Japanese billionaire by about 2023 on a mission around the moon, looping back to Earth. This is certainly on the cards, and it shows the new potential for a much wider group of people to get involved. Now, they're still going to be rich. Closer to home, Virgin Galactic. Virgin has really pushed through with the idea of suborbital tourism. And the idea is that if you pay around 150,000 to 200,000 pounds, you ride in this small spacecraft that's carried by a mothership to 45,000 feet, and you'll see what happens. These images were taken on the third test flight of this about 3 months ago. And on this particular flight, piloted by a British pilot, David Mackay, the vehicle got to Mach 3+, and at engine cutoff, it kept going up. It reached an altitude of 170,000 feet. It was so high up that you'll see in some of the images, it wasn't able to use aerodynamic controllers, it was using reaction control thrusters. And even I, as a long-time cynic of what Virgin Galactic was trying to do, have turned around in my opinions on this. Whether or not it'll be viable as a business model, I don't know, but I'm confident that in the next few months, we will see on a test flight Virgin Galactic reaching the boundary of space as part of its test program.
Well, that is $1 million view out the window, Dave. Maybe the all first, Dave. Yeah.
And then gliding back to Earth in a feathered configuration and landing safely. The lecture before me, though, was focused on Mars. And in this messy slide, I'm going to try and explain in 1 minute, in my last section, what is it about Mars that has such a pull on the human psyche? Well, Earth and Mars are worlds as different as they are alike. In many ways, Mars is more moon-like than the Earth. We've got an atmosphere, but the planet is battered by craters. It's got enough wind power to power dust devils, but when you look at the surface of Mars, it might look like a desert on Earth. The air pressure is the same as the air pressure on Earth at an altitude of 120,000 feet. Liquid water poured out on the surface of Mars would freeze and boil away. You can't have river systems on the surface of Mars. We have enormous volcanoes the size of the United Kingdom. We've got frozen water, all right, but this is a world with almost no atmosphere. But when we look at the surface, we see sedimentary rocks. We see ancient river systems covering an area the size of Wales. All of that tells us, billions of years ago, Mars was much warmer, much wetter, had a denser atmosphere, and the big challenge for us is to find out whether or not there was ever life on Mars. Now, no spacecraft has yet returned samples of Mars back to Earth, but we have got Martian meteorites, pieces of the surface of Mars blasted off by asteroid collisions that have ended up on Earth. In one of my pockets, I have a sample of one of them. It's just a few grains of the Nakla meteorite. And what's so special about this is when you put it under an electron microscope, some astrobiologists are saying they are seeing evidence of ancient bacterial life on Mars. You know, as a scientist, I want this to be evidence of past life on Mars, but I must say there are other explanations as well. And this, to me, is the reason why we've got to send humans to Mars, to answer the question of whether life ever got started there. That is why the European Space Agency and NASA have a roadmap of going back to the moon, exploring Mars with robots, and ultimately sending humans. And you might say, well, why do we send humans when robots can do a job? This is the Curiosity rover that's been trundling over the surface of Gale Crater for 6 years, rewriting their textbooks about methane emission on the surface. Why bother with humans? Well, what I'd say is look at the story of Jack Schmitt. 1972, the only geologist to go to the moon. He was on the last mission. On the 3 days he spent on the lunar surface with Eugene Cernan with a lunar rover, they covered twice the distance that Curiosity has covered in 6 years. Robots are great, but there is no substitute for having a human field observer there with the most sophisticated computer system we know on site. And so when will this become a reality? I think it will be within the next 20 years, and I'm convinced that it will be an international endeavor, which means right now, of course, in primary and secondary schools around the world, we have a bunch of young students who have no idea that they are going to be taking the next giant leaps for humanity. That is the ultimate goal, but I'd like to conclude with a different perspective. Will we ever see sustainable human bases on Mars, certainly in the next 20 years? I don't think so. And the reason I say that is encapsulated by this wonderful image taken by the Lunar Reconnaissance Orbiter. When we look at this image, we see a planet, in terms of Earth, that is unique in the solar system. Because Earth is a planet on which life has been teeming for billions of years. Life has fundamentally changed the geology of the planet. It's fundamentally changed our atmosphere. And no matter where we look in the solar system, look at the surface of Mars, Mars is orders of magnitude more challenging than Antarctica. And so for me, if we're going to get sustainable bases, it's got to be somewhere closer to start with. It's got to be on the surface of the moon, because if anything goes wrong there, you are only 3 days away from Earth. As the Apollo 12 command module pilot, Dick Gordon, said, we went all of the way to the moon, and the most astonishing thing we discovered was planet Earth. No matter where we go in future, we will always have written fundamentally within our mindset the conditions here on Earth. And I want to conclude with the first words spoken on the lunar surface by the Apollo 15 commander, Dave Scott. This mission, the 4th successful lunar mission, landed in arguably the most beautiful landing site, the Valley of Hadley-Apennine. And these were his first words on the surface of the moon. As I stand here today, I'm reminded of a fundamental truth. Humanity must explore. And this is exploration at its greatest. Now, for a long time, I thought he was referring to space exploration, but I now think he was referring to the voyage of exploration that the human race has only been able to achieve through harnessing the critical thinking skills and the knowledge acquisition of science, technology, engineering, and medicine. And if we are to continue that development, that story for the next generation, it is vital that we inspire and we support the next generation of scientists and engineers. That's why it's been such a pleasure and a privilege to be able to talk to all of you today. Ladies and gentlemen, thank you.